Welcome back. Let's finish up some generalized linear model stuff today. Last time we talked about using the logit link function, which was based on the log of the odds ratio, and that was appropriate when we had binomial data. Again, binomial data, you'll know when you have it because it's a discrete distribution. It's only going to be integers, and there's a fixed number of trials. If you recall back into the beginning of the semester, we also talked about the Poisson distribution, where there wasn't a set limited number of trials, but we were counting things that were relatively rare. I think the example that we used in class was the number of bears per hectare in the Smoky Mountains. And so recall that the Poisson distribution is described by a single parameter called lambda, and the maximum likelihood estimate for lambda was just simply the mean of all of our counts that we had taken. And so if we have data that are distributed as Poisson random variables, it would make sense that we would want to appropriately model our data as being random variables drawn from a Poisson distribution. And so we can put this into a generalized linear modeling framework, much like we did with the binomial data, where we use the logit function, the logit link function. For a Poisson, the link function is what's called a log link function. And it's just simply that we can get the log of the parameter of interest as being some function of our intercept and our slopes, however complicated we decide that we want to make that model. So it's often shown in books and stuff, if we're thinking about a log link, remember we use that little lowercase g a lot of times to talk about the link function, and that's just simply the log of mu. And here mu is the parameter of interest, and ultimately what it's going to give us is the expected number of individuals. Okay, and so let's go ahead and just kind of prove to ourselves that that is indeed what we can extract out of there. Let's make me small. Make me small. There we go. So I'm going to do what I like to do, which is simulate some data, because when we simulate data, we know the real answer. So I'm going to set my number seed for those of you playing along at home, and then I'm going to take 100 random variables from a Poisson distribution with a lambda equal to 2. And recall again that the lambda is often referred to as the rate parameter. So it describes ultimately what the expected number should be if we plug it into a Poisson distribution. So I'm going to go ahead and I'll run that. And there's our 100 random variables drawn from a Poisson distribution. And we know that if we wanted to estimate the parameter lambda based upon those data, all we would do is we would just take the mean of dat, and that would be our maximum likelihood estimate for the parameter lambda. And again, since we simulated this data, we know that the true population lambda is 2. Based upon our sample of 100 individuals, our maximum likelihood estimate for the parameter lambda is 2.04. And of course, the law of large numbers would apply here. If we took thousands of samples, we'd get closer and closer to that true value of 2. So we could also estimate it the same way in just a more formal way by popping it into a generalized linear model. So if I were to say mod is going to get a GLM, which is going to tell R I want to do a generalized linear model. And what I'm going to do is I'm going to just estimate the intercept. So just like when we were playing around with general linear models, if all you do is estimate the intercept, then all you're really doing is you're estimating the mean in a general linear model. Here we're going to use a generalized linear model where we're only going to estimate the intercept, and we should be able to get the same estimate that we got when we took the maximum likelihood estimate right there. And so all I have to do is tell R that I would like this to be modeled as a Poisson. So I go ahead and I run that, and let's go ahead and look at our model. And here is the parameter estimate from our model. Now we remember that this is our link function, and so what we would need to do is we'd need to exponentiate that to get our estimate of lambda. And so I'll just go ahead and I will take our parameter value and I will exponentiate it. And there we have it, 2.039898. Okay, and so I mainly did this to just like we did with the binomial error structure, is just so that we feel comfortable about how we should be interpreting those parameters and reminding ourselves that the parameter estimates are done using this link function, and so we would need to transform them if we want to understand them in the units at which we might want to describe things. And so based upon our model here, the expected number of observations that you would make randomly sampling from that population is 2.039. That is the parameter lambda. And so as long as we feel comfortable with understanding that we're dealing with this link function, everything else of a generalized linear model is entirely consistent with what we've done earlier in the semester when we played around with general linear models. And so as an exercise, just to kind of go through and make sure that we feel comfortable about this, I'm going to load in some data that is called Poisson because it's fun. And then we can go ahead and we can look at these data. And what are they? So these data are based upon sampling crayfish in aquatic habitats, obviously. And what we're ultimately interested in this problem is we would like to come up with a model where we can predict the number of crayfish per square meter. And so that's what this column is here. This is the number of crayfish that you would see per square meter across all of these different habitats. And what do we have here? In total, we have 200 observations. And then you'll notice that we also have a couple of factors that we might want to include in the model to see whether or not we can do even a better job at predicting the number of crayfish. And so we have two different things here. We have habitat, whether or not it was in the mid-depth of a lake or whether or not it was what I'm calling benthic, which would be deeper in the water. And then there's littoral, which would be at or near the edge of the pond. And then we've also measured the amount of cover. Those of you that have ever gone out catching crayfish, you know that they generally like to hide under things. And so we have an estimate of the amount of cover in every one of these quadrats that we went to. And so what we'd like to do is set up a model where the number of crayfish is going to be some function of habitat and some function of cover. And so to start, let's just start with a simpler model just to make sure that we feel good about our parameter estimates and what we're going to be doing. So I'm going to start with a very simple model where we're only going to include cover. And we can look and see what those data look like. I'll go ahead and I will plot those. And this is what our data look like. So first of all, eyeballing this, you would know never to be tempted to model this as being random variables drawn from a normal distribution. Number of crayfish, you can't have less than 0 crayfish. And this is clearly integers, right? You can't have a half a crayfish. Well, I guess in principle you could if it had a bad run-in with a fish or something. But for our purposes, we'll pretend that they're happy, healthy crayfish. And so they're only, integers here. So it would be entirely inappropriate to model these as being random variables drawn from a normal distribution. But again, as long as we understand how sampling distributions work and use our noggins and think about the data, it's pretty clear that this, or at least a first good attempt at this, would be to do it as a Poisson process because we're counting things. And there's a lot of quadrats that have 0 crayfish. And so that, to me, just screams, try Poisson, just like that. Okay, and so let's go ahead and we'll set up a simple model where it's going to be a generalized linear model where we're going to think about the number of crayfish, number crayfish is going to be some function of cover. And then we'll ask it kindly that we are going to do family is the Poisson distribution. And that way R will know that we want to do a log link function. And our data is dat. And so we go ahead and we do that. And what do we have? Let's take a peek-sees here. So here's our model. Here's the parameter estimates from our model, reminding ourselves that they're in this log link units or on a log link scale. The first thing we might want to do, which is always a good idea with general linear models, is to take a look and make sure that we're happy with where our deviance is. Okay, so again, the deviance is a variance component thing. You would really kind of like it if your residual deviance, which here they're talking about the model that's including the predictor cover, you would like it in principle to be less than or really close to the actual degrees of freedom that are present. If it's a lot greater than that, that would mean that you're suffering from what's called over-dispersion. And over-dispersion happens frequently, actually, with Poisson and to a lesser extent binomials, because we have a single parameter that's describing both the mean and the variance. So there's a theoretical expectation of how much the uncertainty should increase as we increase the value, the expected number of crayfish in this case. Frequently with Poissons, they are what are called over-dispersed, meaning that the data themselves, the variance is increasing greater than the mean or the expected value, but it's not able to be included in the Poisson distribution. And we'll talk about how to deal with over-dispersion next time, briefly. But we could check and see how good we feel about this particular deviance by popping it into a chi-squared distribution, where we will have 204.02, and we will have 198 degrees of freedom. And we will say lower tail equals false. And that would be the p-value. So that means that our data are not significantly different from our predicted values. So our model's doing a good job at actually predicting our data. And that should make us definitely feel pretty good. So once we got to that point, then we could start to think about the hypothesis testing part. So we could go ahead and we could load in that package car, which we have used a lot. And I'm going to go ahead and do an ANOVA on our model. And it's going to do that likelihood ratio test for us, the deviance, analysis of deviance. And that's our p-value associated with that. So that's telling us that it's actually a pretty good job for us to continue to include cover in there as a predictor, as opposed to just saying cover doesn't matter and all we can do is estimate that parameter for lambda. And since we have our parameter estimates right up here, we could pop that in to a formula, right? And so it's just like we had done with any other linear model. Here we have our intercept, which is negative 5.333532. And we can add to that our cover slope, which is 0.086166. And then for any given value of cover, we should be able to predict the number of crayfish we'd be able to see. So let's say that cover was, let's say, 40. And then reminding ourselves that we are in this log link land, so we're going to need to exponentiate those values, that value. And so we go ahead and we do that. And what do we expect? On average, if cover is 40, we expect to see 0.15 crayfish per quadrat. So not very many. That means that we're expecting a lot of zeros when we only have cover of 40. But we could go ahead and we could crank it up a little bit. Well, what happens if we had a cover of, say, 70? And we'll pop that into our model. Now we're expecting roughly 2 crayfish every time we go to a quadrat that has much higher cover, has a cover of 70. And so we could do that for any possible value of our covers. And we could go ahead and here's our raw data again. And we could lay on top of that points. I'm going to lay points on top of that. And I am going to, I got to look at my DAT again. Got to remember where I'm at. Okay, DAT is, the third column is the amount of cover. Yes, yes. And so I'm going to say that I want DAT, $, cover. On the x-axis, Now the y-axis, I want it to be the predicted values. And so instead of doing something really cumbersome like this for each one of those possible values for the cover, I can go back and use that predict function, which we've used before. And so I'll go ahead and I will say predict what? Predict my model. And the type of prediction I want is the response. It's the expected value. And then to make it pop out a little bit, I'm going to say that the PCH is 19. PCH simply means the plotting character. And then on top of that, I'm going to tell it that I want it to be red. PCH of 19 is a solid circle is all. So I'll go ahead and I'll do that. And now we can look at what our model is predicting. So again, the black dots here are observed data. And the red line there, or the red dots there, are the expected number of crayfish you would expect to see as a function of cover. So again, it's a nice little kind of curvy relationship. Just because it's a curvy relationship does not mean that it's not a linear model, because these are generalized linear models. Again, reminding ourselves that all it means is if you're a linear model, you're not multiplying parameters by other parameters, and no parameter is serving as an exponent to another parameter. Okay, so, but let's go back to our data, because sure, we had the cover stuff in there, and that's pretty neat. I would argue it's neat. But we also have habitat, so we might want to know whether or not habitat matters as well as cover. So, you know, is cover equally important at shallow depths versus deep depths? And so we can go ahead and I'll just make another model where I will call this one model 1. Sure. And I'm going to add habitat in there. Habitat. I'm going to include the interaction term in there so that way I feel comfortable when it comes time to do the hypothesis testing part of it to make sure that there's no nonlinearity between the effective cover and habitat. But this is very similar to what we did whenever we set up a standard linear model. And so I'll go ahead and I'll run that. And then we can go ahead and do the summary of mod 1. Okay. I won't even bother testing for the deviance in this case because it's less than the degrees of freedom, which means I already know what the answer is going to be, which is that our model is doing a very nice job. We have our parameter estimates up here, and we could go ahead and let's do an ANOVA on mod 1. And we see that cover is popping up as being important and worth keeping in the model, as is habitat important and worth keeping in the model. Cover by habitat, the interaction term, is not significant. And so what I'm going to do is I'm going to just drop that from the model because all I'm doing is sucking up some degrees of freedom by including it, and it's not contributing at all to our understanding of the number of crayfish. So you could either do it that way, which is just probably the better way for a simple model like this to kind of look at it and say, I really don't need that interaction term in there. Could also have used the step function that's built in, step mod 1. And step mod 1 is going to drop the interaction term and decide that the best model is indeed the model where cover and habitat are in there, but there is no interaction. So either of those approaches are fine. Frankly, you could keep the interaction term in there if you wanted to. It's your model. You can do whatever you want with your model. It's not wrong to keep the interaction term in there. You're just potentially compromising your statistical power a little bit because you're adding extra parameters to the model, which again, if you decrease or if you increase the number of parameters in the model, the greater the uncertainty around your estimates are going to be, which could compromise your statistical hypothesis testing power. And so let's go ahead and just drop that and make that a plus. Okay, again, now we have a model where there is no interaction term. We have a parameter estimate for cover. We also have, again, parameter estimates for the littoral and the mid-depth. And everything's going to be relative to benthos, right? Because the same kind of dummy coding that we've done before is happening here. And alphabetically speaking, habitat benthos or benthic environments alphabetically are first, so it becomes the first factor level. and everything is going to be measured against that first factor level. And so we have our model now. We can run our ANOVA on our model, and this would be our conclusion that both cover and habitat are indeed important. And so going back, we can graph it. Okay, so there again is all of our raw data. And then given that we have our parameter estimates, mod 1, there's our parameter estimates right there. Okay, we can go ahead and we could add points then for each one. And so what I'm going to do is I'm going to cut and paste this. So on the x-axis is going to be the amount of cover for each of those. And then here again is our model. Okay, it's going to be exponentiated because we're dealing here with this log link function, but everybody gets the intercept. Okay, maybe make that look a little bit. Can I make that look prettier? There we go. There is the parameter estimate for cover, and everybody's got cover, so we're going to add to that. Here's the parameter, the slope for that, times the amount of cover that was actually present. And again, the amount of cover is just that third column, which are all these different values right here. And then first, if we're doing it for benthic organisms, we're going to take the slope estimate for if you're in littoral, which is right here, and we're going to multiply it by 0 because this is dummy coding again. Think of them as switches, turning them on and turning them off. First, I'm going to try to plot out stuff for benthic. So that parameter is going to be turned off, and this parameter is going to be turned off. So I go ahead and I'll do that, and there we see our predicted values now for if you're in the benthos. And we could do the exact same thing then for the littoral habitat, I believe that is. Yep, there's the parameter estimate for the littoral habitat. And so this time that parameter is going to be included in there. Everybody gets the intercept, everybody gets the slope associated with cover, but now we're going to include, hey, I'm in the littoral habitat, we're going to include that parameter, and then I'm not in the mid-depth habitat, so we're going to exclude that parameter. Go ahead and we do that. And so now the blue is the littoral habitat. And then I will go ahead and do that for one last one, which is going to be for the mid-depth habitat. And so again, everybody's going to get the intercept, everybody gets the slope associated with the amount of cover. Because we're interested here in mid-depth, we are going to multiply the parameter for littoral by 0. Again, switches on and off. And then we're going to add to it the parameter for mid-depth. Go ahead and we do that. So now let me make that a little bit bigger so we can see it a little bit better. Okay, and so the red here is benthic, the green here is mid-depth, and the blue there is littoral habitats. Those are our 3 different expected values for each of those. Okay, we could also plot, and this is posted with the code, so we don't have to go through it, but instead of doing that, what I can do is draw lines, because it might look fancier. Looks something like that. And so now we can see the relationship between cover and the amount of, you can even put a fancy little, look at that. And so we can look at these lines then and understand how cover influences the number of crayfish as well as habitat influences the number of crayfish. So if you're in a benthic area, the amount of cover doesn't matter as much compared to if you're in a littoral area. And yeah. And so Again, all the different steps involved with this are very similar to what we've been doing with all the other models. The only thing that we have to think about and be careful about is first decide what kind of, how you want to model your data. In this case, we decided we were going to model it as a Poisson, have some understanding of how that length function is working so that we can interpret our parameters. And then once we have that, we can proceed just as we had done with any other kind of linear model where we are doing hypothesis testing. And so once you can get your head around how the length functions are working, generalized linear models are really, as much of a piece of cake, I guess, as any of the other models that we've been playing with up to this point. Okay, well that wraps up the Poisson generalized linear models. I hope you enjoyed that. That one was actually pretty short because, again, once you understand the length function, it's just a linear model. You just got to remind yourself what kind of a length function you're dealing with. Okay, well that's it for the Poisson by itself. And what we'll do next time is briefly talk about what happens if you do have a problem with over-dispersion and your deviance is really big. And spoiler alert, it's going to be kind of an open-ended lecture because there's a lot of different things you can do, and I just want to introduce some of those concepts to you. That's all. I will see you guys shortly. Okay, one last little finishing touch that I want to put on to GLMs, to generalized linear modeling. And that is this problem that we've been kind of avoiding conveniently of over-dispersion. And so again, to remind ourselves, things like the binomial and the Poisson distribution have a single parameter that captures both the location and spread in one parameter. And so there's a theoretical expectation of what the variance should be around a binomial sample, and there's a theoretical expectation of what variance should be around a Poisson sample. But as it turns out in the real world, oftentimes we have more variance than our model assumes that there should be. And so this is the phenomenon that's called over-dispersion, and it's a pretty common problem, especially with Poisson distributions. And so I just wanted to really briefly talk about an approach that one can take within the GLM framework with the function GLM, and then just really quickly introduce another distribution just so that you're aware of it. It's increasingly becoming a common distribution to use for Poisson type count data when you have problems of over-dispersion. And so I'm just going to go through the little bit that we have in the notes that I've posted. And here you can see I cleverly said some quick thoughts on over-dispersion. So again, that we know what over-dispersion is then, and we know what the problem might look like, and we know how to diagnose the problem. So here I'll just read in some data, which I'm going to decide to model as a Poisson. And I'll go ahead and I'll make a linear model, a generalized linear model. And just as the example before, I'm just going to estimate the intercept. So all I really want to do is be able to estimate what that lambda parameter is. And we know what the point estimate is for that, because all we have to take is the mean, and that is our maximum likelihood estimate for the parameter lambda that these data were drawn from. But when it comes to statistical hypothesis testing, we also want to incorporate the uncertainty around that point estimate. And that's where over-dispersion becomes a problem because, again, if your lambda is 2.4, there is a closed form solution of what you expect the uncertainty to be around that. And if our data are over-dispersed, that means that we have more variation than the distribution is actually predicting, which means that when we're doing our hypothesis testing, that we are reducing, we are deflating the amount of uncertainty around our point estimate, which is going to increase our type 1 error rate, and it's basically just bad form because we're going to be making one assumption about a certain variance, and it actually could be larger. And so I'm going to go ahead and I'm going to run that, and then I will go ahead and I will look at the summary of this model. And here again, our first check that we want to look at is the deviance. And so here, the deviance, I'm seeing that it's a little bit bigger than the degrees of freedom. So maybe I want to check out and see what that looks like. And so I can go p chi-square 70.094 with 49 degrees of freedom, lower tail equals false. So I do that and I get 0.025. And so that's the p-value for using that chi-square distribution, which means that if we stick with a threshold of 0.05, that means that our observed data are significantly different from our predicted data from the model. And that's not terribly satisfying because we would like we'd like to be able to trust any hypothesis testing that we might do. So one solution to this are what are called quasi-distributions. And quasi-distributions were developed explicitly for this problem of over-dispersion. And all that's happening in a quasi-distribution is that the computer is going to iteratively calculate what is a dispersion parameter that will serve as a multiplier so that we will increase the standard error around our point estimate of our parameter. And so you can see as the default when we use family Poisson that the dispersion parameter is taken to be 1. And that means that we know what the variance should be across the Poisson distribution or for that Poisson distribution. And we should be able to model then effectively our data. But since we have this over-dispersion problem, it's very clear that actually that probably isn't the case. And so we need to account for that. And we account for that by using what's called a quasi-distribution. And there's also a quasi-distribution for a binomial built into the GLM. But we'll go ahead and we'll use the one for a Poisson. And it's simply family equals quasi-Poisson. So I'll go ahead and I'll run that. And now I will look at what our output is. And so first you can see that we no longer have a dispersion parameter that is 1. Instead it's 1.19. And so that's going to serve as a corrector, if you will, a correction factor for the uncertainty around our standard error, or for around the variance around our parameter estimate. And so if we go back and we remind ourselves what, this is using just the Poisson distribution here, notice that this is our standard error, 0.09129. When we use the quasi-distribution, our standard error has now increased and it's 0.0996. Now granted, that's a pretty small difference, but it's still a difference. And if your data are highly over-dispersed, which sometimes can happen in pretty dramatic fashion, you can end up with a very, very large dispersion parameter. And what that's going to allow you to do is to do honest hypothesis testing because you're going to be accounting for that extra uncertainty around your parameters. And to demonstrate that that's all this dispersion parameter is I, here over here I've taken, that's the dispersion parameter. And then this is our standard error estimate from the over-dispersed model, which again is our model based upon just a Poisson. So that's where that 0.09129 is from. So if I take that standard errors are in what? They are in units of standard deviations. Deviance is in units of variance. And so we'll take the square root of our dispersion parameter and we'll multiply that by the standard error of the original Poisson model. And what we end up with, as you see here, is the same value. So basically that's what the computer is doing behind the scenes, is it's estimating the dispersion parameter, and then it's taking the standard error of the straight up Poisson model, and it's multiplying that standard error by the square root of the dispersion parameter, and that's giving us our new standard error. So our standard error has increased. Our standard error has increased, which means that we're less likely to commit a type 1 error. Because now we're effectively modeling the uncertainty around our point estimate. And so that's in the general sense of how these quasi-distributions work. Note that our deviance has not changed, and that's because there is no closed form probability mass function for a quasi-Poisson distribution. Rather, we're fitting a Poisson to it, and then the computer is figuring out some penalty term, essentially, which is what the dispersion parameter is, which is why you will not get an AIC when you use a quasi-distribution, because there is no likelihood for the whole model. Now, if you dig deep enough and you're that interested in quasi distributions, there are packages that estimate likelihood. They come up with a quasi-likelihood so that you could calculate a quasi-AIC if you're so keen on doing such a thing. I think that's a little bit, as I said, there could be a whole class just on generalized linear models, but this is a very common problem that people run into, so it was worth being familiar with it. The other solution, if you have over-dispersion, is to pick a different sampling distribution. Again, all we've played with is binomial and Poisson, but there's a number of different distributions that we could potentially model our data as. And so one that I wanted to mention, because it's actually becoming increasingly more commonly used, especially when people are counting like reads, for example, of microbial data sets or whatever they might be, where you're actually counting the number of reads per microbe and then you're trying to model that. So it is count, but very frequently that'll end up with an over-dispersed distribution. And so the distribution is called a negative binomial, and it's similar. It's more similar to a Poisson. Actually, the Poisson is a special case of a negative binomial than it is to a binomial, which is maybe counterintuitive. But what the negative binomial is modeling, it is you imagine that you have a binomial sampling procedure, and you have a particular probability, and we've already done this. So if you were to do, if you flip a coin 20 times, you have an expected number of heads or whatever it might be. How the negative binomial works is it is the expected number of successes until you get to a set number of failures. So maybe you're trying to estimate, how many heads will I get before I get 5 tails? And then as soon as I get 5 tails, I'm done, and all I'm doing is counting up the number of heads. It's used very frequently for things that have to do with rates as well. Without getting too much into the weeds, the probability mass function for a negative binomial, I just wanted to point out that the negative binomial does indeed exist, which is a nice thing. But we can set one up. Within the package mass, there is a function called GLMnb, which stands for Generalized Linear Model with a Negative Binomial Error Structure. And I'm going to take our exact same data as before, and I'm going to just go ahead and I'm going to run it into there. And then I'm going to look at the summary. And so here we have our estimates. We have a dispersion parameter. This dispersion parameter is actually just a parameter that this is the expectation that's within the probability mass function for a negative binomial, which means that we actually are now getting a likelihood. And as such, we would have an AIC, so we could, if we wanted to, we could compare various models. But what I want to point out is here, if we were to look at the residual deviance and see whether or not we're over dispersed, we can pop that in there, and then that would be the p-value. So we would accept the null hypothesis that our observed data is the same as our predicted data based upon the model. So there are these other distributions out there, and we're not going to do anything about a negative binomial in the class, and certainly won't be on the final or anything like that. I just wanted you to be aware that there are these other distributions that you could potentially use. Hopefully, you feel comfortable enough now with how to put together linear models, and you understand, at least conceptually, what's happening with link functions with generalized linear models, that if you get to that point, where you have your own data and you have over dispersion and you're concerned about it, you could either dive in on your own and think about what alternatives there might be for coming up with an appropriate distribution for the error structure, The quasi is always fine, and it's there, and people use that quite frequently. But more important, if you understand the language of how generalized linear models are working, and as long as you're kind of committed to making sure that you understand what those parameter estimates are going to be, that's where you could go in and talk to somebody, talk to a statistical consultant and ask the right questions, because that, you already have hopefully enough foundation where you can specifically ask the question. You can say, hey, I have this data, I tried to model it as a Poisson, I'm having all these over-dispersion problems. Is there any other alternatives besides a quasi-distribution that is worth trying? If you ask a succinct question like that to a consultant, they're going to be very pleased, because usually what they probably get are people walking in with a bunch of numbers saying, analyze my data. But since we understand how those models are put together now, you can go in there and you can ask the appropriate questions and figure out how to solve that dispersion problem. So that's it. I just wanted to mention on how we're going to deal with, or how we might deal with, the problem of overdispersion. So yeah, that's generalized linear models. There's lots of, as I say in the bottom of that PDF, the 2 chapters on generalized linear models in that Michael Crawley R book are actually quite well written, and so we can always return to that if you want to explore a little bit more about these generalized linear models. So at that, I will say so long and good night.